Okay, Organic Chemistry 2. This is Chapter 19, where we talk about aldehydes and ketones and the chemistry of aldehydes and ketones. And the first thing you need to know is what's an aldehyde and what's a ketone. And I think if I was to ask anybody who's hearing the sound of my voice, they would say, well, aldehydes and ketones both possess carbonyl groups. And if the carbonyl is flanked by two R groups, it's a ketone. And if it's flanked by an R group and a hydrogen, then it's an aldehyde. And what's neat is that ketones and aldehydes are kind of ubiquitous in biology and industry, so they're everywhere. What are some aldehydes and ketones that you would know? Well, the simplest possible aldehyde is formaldehyde, and I'm sure that everybody has heard of formaldehyde. It's used as a preservative, and I think that everybody here has heard of acetone, especially if you did the wet lab in Organic Chemistry 1. Sometimes we use acetone to clean dishes when there's stubborn bits of residue that won't come off of glassware. And also, acetone is used as nail polish remover, but in organic chemistry, it can be used as a reactant. It's used as a solvent a lot in organic chemistry. And formaldehyde and acetone are common names, but I expect you to know the formulas and the structures of both and the names of both formaldehyde and acetone. Where else do we find ketones and aldehydes? Well, all kinds of cool um, interesting compounds with interesting odors. Okay, really interesting smells are ketones and aldehydes. I can't put it any other way. So if you like the smell of vanilla, so that comes from vanillin, and you can see that there's an aldehyde in here. Cinnamaldehyde is responsible for the flavor of cinnamon. You can see that there's an aldehyde in here. You also see that we have a transalkene, so trans-cinnamaldehyde. And the next one is R-carbone. There's R and S carbone. S-carbone has the odor of caraway seeds, but if you like the odor of spearmint, like spearmint gum, that's R-carbone, naturally occurring compound. And benzaldehyde has the odor of almonds. So if you like the odor of almonds, benzaldehyde has that. Where else would you find a ketone and aldehyde? Well, in the male and female sex hormones, so progesterone and testosterone, you see that they both end in -one, and they both have a ketone in them. And progesterone even has a second one. And both of these are built on a steroid skeleton. But those are some great examples of where you find ketones and aldehydes. And I'm sure that if you look through any kind of list of marketed drugs, if you look up prescription drugs or illegal drugs, you'll find a whole holy host of compounds that have ketones and aldehydes. And so that is why it's so important that an organic chemist understands the chemistry of ketones and aldehydes, that a chemist knows how to name ketones and aldehydes. If you're an MD and you see the structure of a compound, you want to be able to say, well, that's got a ketone in it, that's got an aldehyde in it. That might react in this way in the human body, that might react in that way. And so let's start by talking about nomenclature. Best thing about nomenclature, and there's lots of cool things about nomenclature, are that the rules don't change. Every few years, IUPAC has a conference, and they might change, a couple of things like really out there. But as far as what we learn in chemistry 3101 and 3111, there's nothing that gets changed in the rules of nomenclature. And so your children and your grandchildren are still going to be using the same rules for naming aldehydes and ketones. And everything that you learned about nomenclature of alkanes, alkenes, alkynes, alcohols, everything is going to help you in naming aldehydes and ketones. What do we do first? We identify the parent chain. Then we identify and name the substituents. Do we have a methyl, an ethyl, a propyl, what have you? Then we assign a locant. A locant is just a tsatzy word for a number. Is it a 3-ethyl? Is it a 4-methyl? Whatever. And then we put everything together alphabetically. We separate numbers and numbers with commas. We separate letters and numbers with hyphens. And there you have it. So let's take a look at some examples. Identify the parent chain. I think that everybody could identify 4 carbons and a hydrocarbon as being butane. Well, if you have a 4-carbon aldehyde, we call that butanal. So the suffix E gets dropped and we replace it with al. Now you might be wondering, why don't you call this 1-butanal? Because that is redundant. We do not need a locant for the aldehyde. We always assume that the aldehyde is at carbon number 1. There's no way to have an aldehyde at carbon number 2. Don't draw that. That's a heresy. Now you've got a carbon with 5 bonds. You would have a ketone And so when you're naming an aldehyde, you do not have to use a locant. Just call it plain old butanal, like Cher or Madonna, right? Just one thing. Anyhow, for an aldehyde, much like an alkene or an alcohol, the parent chain has to contain that carbonyl carbon. Here in this alkane, our parent chain has 8 carbons. And we still have a chain of 8 carbons in this compound, but it doesn't contain the carbonyl group. And so this compound would be 2-propylhexanal, because we have to choose the parent as having the carbonyl group on it. Something our book doesn't do a lot of. It doesn't talk a lot about bifunctional or polyfunctional compounds, but for some reason in this chapter, he decided to address it. And I didn't put all the details in here. But going back to my point about the aldehydic carbon, or the carbon of the carbonyl of your aldehyde, which we call an aldehydic carbon. Anyhow, the aldehydic carbon is assumed to be number 1. And even if you have an alcohol or an alkene, the carbonyl takes precedence over any of those functional groups, like alkenes or alcohols or alkynes. So I don't ask a lot of questions about polyfunctional compounds. However, it's in the book, so I thought I would mention it. Now, when we're talking about ketones, it's a little bit different. It says for a ketone, you drop the E suffix and you replace it with -one. So butane would become butanone. Now, we do use locants for ketones, but you can see that with butanone, you don't need one. Well, why would that be? Because the only place the carbonyl could be would be here or here. And either way, it would be the same compound. It's not till you get to 5 carbons. So let's see here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It's not till you get to 5 carbons that you could have different regioisomers. You could have this compound or this compound. So the one on the top would be 2-pentanone, and the one on pentanone, no, pentanone, and the one on the bottom would be 3-pentanone. Okay, so not until you get to 5 carbons do you have to worry about that. And a neat addendum that they put in the nomenclature rules back in the 90s, I think, or maybe early 2000s, was that instead of calling it 3-pentanone or 2-pentanone, you could call it pentan-2-one or pentan-3-one. And you see that in this example here. We have 3-heptanone, or you could call it heptan-3-one. Either one is perfectly legitimate. They're both perfectly acceptable. Everybody will know what you're talking about. So aldehydes and ketones. Now, of course, if you have a chiral center, right, that's, that was covered in chapter 5 of Organic Chemistry 1, if you need to go back and review the rules of RNS. Of course, if you have a stereocenter, you have to indicate that at the beginning of the name. So let's see here. We've got our longest carbon chain, 1, 2, 3. So we've got a 3-phenyl and a 2-chloro, propanal, right? Instead of propane, you have propanal. So propane, you drop propane, you drop the E and you get propanal. And then the stereochemistry here is R. Let's review to make sure it's correct. We have our hydrogen atom coming out in front. The chlorine is our highest priority. The hydrogen is last. This is second. This is third. So we're going from 1 to 2 to 3, which is counterclockwise, which would be sinister or S. However, since the hydrogen is coming out in front, we reverse that. And so the stereochemistry here is R. And so this looks good to me. The author of the slide was correct. So R, 2-chloro, 3-phenylpropanal. Another funny one that doesn't come up, I shouldn't say funny, but one that doesn't come up a lot is a carbaldehyde, but it kind of does. Every once in a while, I'll mention a carbaldehyde. If you have an aldehyde attached directly to a ring, a cycloalkane ring, we call that a carbaldehyde. So this would be cyclohexane carbaldehyde. All right, so the carbaldehyde is one you need to know. And then IUPAC loves common names of aldehydes and ketones. I told you need to know formaldehyde. Acetaldehyde is another one that comes up all the time, and benzaldehyde. These are all common names, but they're called common names for a reason. It's because chemists love to use them. And so our book doesn't give a complete treatment of common names. I took this from the nursing organic chemistry textbook. So this is it here. So if we have one carbon, the IUPAC name would be methanal, but everybody calls it formaldehyde. It's the common name. If you have two carbons, technically it would be called ethanal, but nobody ever calls it that. Everybody calls it acetaldehyde. Now the next three, going from propanal to butanal to pentanal, those are the IUPAC names. I would say the IUPAC names are used a little more than the common names, but the common names could show up in like DAT review materials or MCAT review materials. And I know that some of you are interested in that. So I put them in here. So propanal, the common name is propionaldehyde. Butanal, the common name is butyraldehyde. And pentanal's common name is even more frustrating. It's valoraldehyde. You can remember valoraldehyde because it starts with the letter V, which is the Roman numeral 5 for 5 carbons. I'm not asking you to memorize these ones here, but I included them because they can show up in review materials. Like student showed me one time, like Kaplan review materials for an MCAT or something, and it had something about propionaldehyde, and the student said, "What's propionaldehyde?" So now you know it's in there. And again, it's funny because they do teach this in nursing level chemistry. Well, with all that in mind, who wants to try naming some aldehydes? We got one aldehyde and 2 ketones. Oof, we've even got 2 chiral centers in here. Well, let's start with the first one. What's the longest chain? Could anybody tell me? I didn't even count it up myself. Could anybody tell me what the parent would be in 19.1a?
Hexane.
It's a hexane, right? Because there's 6 carbons in the chain. So if it would be a hexane and it's an aldehyde, so we would call this a hexanal. So let's scribble down, what was it, hexanal? Hexanal. Right, Nick? And this carbon is assumed to be number 1, the aldehydic carbon. So 1, 2, 3, 4, 5, 6. So what have we got? 5,5-dibromo and 2,2-dimethyl. Well, the bromo is going to come before the methyl because B comes before M. So let me scribble it down up here. So we've got 5,5-dibromo and then 2,2-dimethyl butanal. All right, and that's the name of the compound. Wunderbar, as we say in German. So let me just move this down. The next one, we've got 2 chiral centers.
Would it be hexanal or butanal?
Did I say butanal when I meant hexanal? I was testing you, Nick. Got it right.
I'm glad I was paying attention.
Yeah, so hexanal. I got butanal on the brain, I guess. Anyhow, next one. Let's see our longest carbon chain. Anybody have an idea? What would the parent of this one be called?
Pentanone? Or, well,
So it's got 6, right? So if we count starting from here, 1, 2, 3, 4, 5, 6. So it's some kind of heptanone, and the carbonyl is at number 2. So it's a 2-heptanone, or you could call it a heptantuone. Did I say heptanone when I meant hexanone? Jeepers. So this is some kind of 2-hexanone. I think I'm mulling over those stereocenters in my mind here. So hexanone, like that. And then we've got, what are our substituents? We've got 3 methyl groups. We've got 3, 4, 5 trimethyl, 2 hexanones. So let me scribble that in here. 3, 4, 5 trimethyl, 2 hexanones. So now we need to evaluate the stereochemistry at carbons 3 and 4. Oops, I needed room for a dash there, I guess. There we go. So I'm going to move this over. And let's see if we can evaluate the stereochemistry here. Does anybody know what the stereochemistry is? So let me read all this. We'll do a little practice for the final exam. Could anybody tell me the stereochemistry of this carbon that I have highlighted in yellow? Would that be R or S?
R.
Jeepers. Okay, let's see. This is 4, this is 1, this is 2, this is 3. So 1 to 2 to 3. Yeah, you're right, it's R. Okay, so 3 is R. So let's scribble that down. We've got 3R and then 4 something. R. Nick, did you do the other one? Or anybody? I know my students are pretty fast at this. Let's see, what about this one if I highlight it in green? let's see, I guess this would be 1, this would be 4, this would be 2, this would be 3. So I'm going from 1 to 2 to 3. So this one is S. So we have 3R, 4S, 3,4,5, trimethyl, 2-hexanone. Everybody with me on that one? You can always double check my stereochemistry. Did anybody come up with a name for the last one? The parent here has got a ring in it. So this is not a cyclopentane, right? If you have a 5-membered ring like this is cyclopentane, like that. So if I have a 5-membered ring with a carbonyl on it, you call it cyclo, I can write a little neater than that, cyclopentanone. And thus, the name of this compound, if we number it, we've got 1, 2, 3, 4, 5. We've got 2,2,5,5 tetramethyl cyclopentanone. So let's put that down. 2,2,5,5 tetramethyl cyclopentanone. And again, I don't have to call it one cyclopentanone. That would be redundant. It's assumed that the carbonyl carbon is number 1. So there's no need to provide a locant for it. Any questions about the nomenclature before we move on? And there's some other cool questions. Oh, we have another question about nomenclature. I put something in here about dicarbonyls. So the book doesn't really go into this in a whole lot of detail, but then he asks you some questions about it. If you only have 1 carbonyl in your group, then it ends with -one. If you have 2 carbonyls, then you call it a dione. If you have 3 carbonyls, you call that a trione. And if you have 4, you can probably guess where I'm going. You would call it a tetrone, like that. You don't call it a tetraone, it's a tetrone. So I put an example here. This would be called 2,3-butane dione, right? Because you have a total of 1, 2, 3, 4 carbons. And so if the parent here is cyclohexane, you would call this 1, 2, 3, 4. So you'd call this 1,4-cyclohexane dione because it's a diketone. So let's scribble that in. 1,4-cyclohexane dione. And then the last one is a symmetrical compound. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is some kind of nonane trione. And we have carbonyls at carbons 2, 5, and 8. So this would be 2, 5, 8. Nonane trione. And don't expect a ton of questions about multiple carbonyls, but it might be worth a question or something, something about naming a dicarbonyl. All right. Here we go. So that covers nomenclature. And the next section is just a review of ways that you already learned how to make aldehydes and ketones. So let's just review them, and then we'll be on to something new. How did we learn how to make an aldehyde? Well, if you have a primary alcohol, you've got to be careful because a primary alcohol can be converted into a carboxylic acid if you use a really strong oxidizing agent. So an example of a strong oxidizer would be the potassium permanganate method or using sodium dichromate. Sodium dichromate, sulfuric acid, water. That's going to give you a carboxylic acid. However, if you use PCC oxidation, that will give you an aldehyde. If you use Des-Martin periodinane, that will give you the aldehyde. And this last one here, this is the Swern oxidation. That will also give you an aldehyde. You will not get the carboxylic acid. What about a secondary? Oops, I'm getting ahead of myself. What about ozonolysis? So we said, okay, if you perform ozonolysis, you ozonize a double bond that's got a hydrogen on one of the carbons, and here they're showing 2 hydrogens. You can produce an aldehyde. So the first step is ozone. Second step is dimethyl sulfide. What else? We said that you can prepare an aldehyde by hydroboration and oxidation of a terminal alkyne using a hindered borane. So here you can use 9-BBN, or you can use this R2BH or dicyamyl borane. They all mean the same thing. I told you, I think, that in the ACS book, sometimes they'll do this. They draw a borane like this, like the borane is kind of tied into this giant ring. So this is kind of an ACS way of doing it. It just means a hindered borane. But you end up making an enol here, don't you? You end up producing this compound, this enol, which undergoes tautomerization to give you the aldehyde. What else? How do we make ketones? Okay, oxidation of a secondary alcohol. You can use anything you want. You can use this. You can use desmartin periodinane. You can use PCC. You can use the swern, which is DMSO, and oxalochloride, followed by triethylamine. You can use any of these oxidations. These will all work. You could even use KMNO4 and hydroxide, and then H3O plus in the next step. That'll work too. So any kind of oxidation will oxidize a secondary alcohol to a ketone. Don't have to be fussy about that. Also, ozonolysis of a tri-substituted or a tetra-substituted alkene can give you ketones, depending. So first step, ozone. Second step, DMS. We covered that. What else? Oh, acid catalyzed hydration of a terminal alkyne. So this is a Markovnikov addition, right? Good old Markovnikov, our friend. And so you would produce this enol that looks like this, and then that undergoes tautomerization to give you the ketone. So a little more review. If you need a review of these, this would be found in chapter 9, the alkynes chapter. A lot of the other stuff is found in chapter 8, which is the alkenes chapter. What's next here? Oh, and then how to make a ketone. Well, we learned a new way in chapter 18, which is acylation, Friedel-Crafts acylation. So aromatic rings that are not too strongly deactivated will react with an acyl halide in the presence of a Lewis acid to make an aryl ketone. So if you have a nitro group on here, let's say you had a nitro group, that won't work. Right? That's one of the limitations of Friedel-Crafts, but there we go. It's not deactivated, so we're good to go. And with all that in mind, let's try one more practice problem before we turn our attention to something pretty new. And let's see here. Identify reagents that you could use to oxidize this secondary alcohol to a ketone. Anybody have a favorite? Something that we're like, use this. This is my favorite reagent.
Sodium chromate.
Heck yeah, let's do that. All right, chromic acid. Chromic acid is just it's chromium 6, right? All those chromium reagents, Nick, whether it's CrO3, dichromate, all these, there's lots of different chromium reagents. It's always chromium 6 plus, and it ends up being reduced to chromium 3 plus. Now that's not even covered in our book, but just an interesting thing. So Nick says use sodium dichromate. Sounds good to me. And there we go, sulfuric acid and water. Another one that's easier, I'd say it would be PCC. Just write that. Or you could write DMP for desmartin periodinane, or you could do a Swern reaction. The next one is taking a primary alcohol and making an aldehyde. So we need to be a lot more careful here. And so for that, you'd want to use PCC, or you could use desmartin periodinane, or you could do the Swern. I'll just write down the word Swern. You can look up the conditions. First step is DMSO and oxalochloride. Second step is triethylamine. Okay. What are we on here? C. Does anybody have an idea about this one? Taking the terminal alkyne and making a methyl ketone? What conditions would I use for that? There's a special reagent that only really shows up in this reaction, I think, in the book.
H2SO4, H2O, and HGSO4.
Absolutely. Yep. It's mercury 2 sulfate, right? It's the only time this compound ever shows up, right, Lindsay? Is in this. I can't think of anywhere else where HGSO4 shows up in this book. So there we go. Absolutely. And then the last one is anti-Markovnikov addition of water to make an enol that tautomerizes to give you an aldehyde. So the first step will be, we'll just write here 9 BBN, and you could pick whatever hindered borane you like. And in the second step, we use sodium hydroxide and hydrogen peroxide. So what's kind of cool, about stepping into chapter 19, which is a long chapter, is at least you know a bunch of ways to make an aldehyde or a ketone already. So it's, that's not new. You get a whole bunch of cool ways to do that. So what we're going to look at next will be nucleophilic addition reactions. And this is kind of where the chapter gets into new territory aside from nomenclature. And so why don't we take a short break, and then we're going to come back and tackle this section and talk about why carbonyls like aldehydes and ketones are so susceptible to nucleophilic attack. And there we go.